Hi guys, welcome back to the channel. Now what I have here is Ben Eater's 8-bit breadboard computer that I've built out from the kit that he sells on his website. And what I have built out is the first three kits. So the kit comes in, you have here the clock module, the registers, an ALU, the RAM and program counter, and I've built just a little bit of kit 4, the last kit. I've just built out the output. What's remaining is now just the control logic. But before I build the control logic, I just wanted to talk about this build a little bit. One of the reasons why I got this kit was, I think it was right after my digital electronics, after taking my digital electronics course. I wasn't particularly excited about that class, and I felt like I wanted to do much more. I wanted to learn more, and I'm more of a practical oriented person. So what I decided to buy the kit. I think I had watched a couple of his videos and I saw the videos were pretty cool, and I wanted just to build it and have a hands-on experience, because there's something particularly for me that I enjoy about learning when you're doing stuff hands-on, because you run into problems and you read more, and then you also appreciate the theory more. So I'm usually like learn a little bit of the practical, then come back and build your theoretical knowledge. And I can say, in as much as that, I have really learned a lot. I have learned a whole new level of appreciation for digital electronics, and so many different kinds of things kind of like make more sense to me. Like I have an appreciation for stuff like flip-flops, because if you just look at a flip-flop in terms of just its truth table, that's one thing. But when you actually are building stuff with the flip-flops and dealing with counters and those kinds of concepts, when they're actually actualized, they actually are interesting. So right here, one thing I just want to state out is, like, I'm not going to do a full tutorial about what this is. I'm not going to go into details. I think the main purpose of this video is, let's say, I'm going to put it in the sense that it's more of to entice someone to see what digital electronics is all about, the cool stuff that you can do. It's more of like, let's say, for instance, you want to learn about digital electronics, but you don't know, but you're looking for inspiration. Say that you're looking for inspiration. So that's what this video is supposed to be. Or you've learned something and you just want to see, just to push you further to get a little bit more curious about Digital Electronics. This is a video that I think I personally would have loved to have seen, especially when going through the hell of Digital Electronics class. Being able to see what the knowledge actually does, it's kind of like exciting. So maybe the other thing to note is, while this is Ben Eater's kit, the architecture is kind of like inspired from the Digital Computer Electronics book by Albert Malvino, and this is what he calls a simple as possible computer. So this is a very, very simple computer which just runs very simple instructions, and it's just to get you a little bit excited and a little bit inspired to see what happens at the very, very low level. This is not what this is not like what your computer runs, your Core i7 or whatever runs, but this is just at the very, very low level. So just getting through, let's just talk about the architecture of that we have over here. So first of all, the most important thing for me, I would say, is the clock module. So here on the clock module is just is made of a 555 timer. So it just provides clock signals to the various registers in the computer. So after the clock module we have the RAM. So over here we have the RAM. So this is the memory address register, which is used to access the contents in the RAM. And this is where we see the RAM contents. The RAM is a 16x8 RAM, meaning it has 16 memory addresses or memory locations, and the 8 is in each location you can store 8 bits. After the RAM, right below the RAM, we have the instruction register. So in the instruction register, this is where now the instructions that are stored, or whatever instruction you want to run, you load it into the instruction register for it to be executed. Next up over here, we have a program counter. The program counter just basically keeps track of what instruction are we executing, because we have to execute the instructions sequentially. After the program counter, we have our register A. A register A is just basically, call it register A or the accumulator. So this is where we will be, whatever operations we'll be doing, it will be accumulated here. So this is where we'll get our result from. Then we have register B. Register B just stores temporary data that we want to either add or subtract from register A. Then in the middle here we have the sum register, which does some arithmetic. So it's kind of like our arithmetic logic unit. So the ALU, this sum register, it can either add to the to register A, or it can subtract from register A. And then finally we have our output over here. So this is our output that outputs whatever data that, because it takes data from the bus and outputs it, because this is now in binary, and it outputs it in decimal form. Now, just something to mention down here, there's space down here. What's supposed to go here is now the control logic. So I wanted to make this video before I build the control logic, because when we deal with the control logic, the system is more or less automated. Okay, so maybe just a couple of things. No, maybe the other thing to note here is this is the bus. I think that's one of the things that I think I kind of like appreciated more after building this. This over here is the bus, and the bus is just basically, I think the definition is a communication system that transfers data between components inside of a computer. So basically what happens is, if you want to move data from one register to another, you typically load the data into the bus. Let's say, for instance, you want to take, this is the RAM, you want to put the maybe a particular memory content from the RAM and put it into register A. So you put the content into the bus, then from the bus you read into register A, and then that's how you now transfer the data from one section, one register to another. So that's what a bus looks like. More often than not, we just usually used to seeing the bus as some kind of an arrow. So that is the bus. And then another interesting thing is, if you get into it, this over here is an EEPROM, electrically erased programmable read-only memory. So some interesting stuff is done by the EEPROM. If you want to learn more about that, you can just look for the particular video from Ben Eater. So that's just a rundown of what the architecture is. So what I want to do now is just run a simple program, all right? A simple program about to just see the operation of the computer and see how data moves from one section of the computer to another section. I think that would be, pretty interesting. So let me just power it up, and then we can get started. So now we've booted into the computer, and right now here's the clock. I've set it to manual mode so that the clock only progresses when pulses when I push the push button, but of course we can have it in auto mode. But for now, since I'm going to be doing most of the programming and I don't have the control logic, I'm going to be programming the board manually, going step by step. I just have it on manual mode, whereby I have to click the push button to advance. So let's just talk about what we're going to do. So for our simple computer, what we want to do is, well, first of all, you have to define what are the instructions for this particular computer. So for this particular computer, we have 5 instructions that we want to carry out. We want to be able to load data into the accumulator. We want to be able to add data into the accumulator or subtract data from the accumulator. We want to output, once you finish, we want to output our data onto our output, and at the very end we want to halt the system. And for each of these instructions, there's, let's say, we assign it a value. So for instance, for loading, we have 000, For adding, we can have 0, 0, 0, 1. For subtracting, 0, 0, 1, 0. And for the out, we have 1, 1, 1, 0. And for halting the system is 1, 1, 1, 1. So what we want to evaluate today is we want to evaluate the expression 16 plus 24 minus 32. And we want to see what that gives us. Of course, this simple arithmetic we know is going to give us 8. But now let's see, how does a computer deal with all this? So now let's talk about how do you program the computer. So what happens is we have our RAM. We have our RAM, right? And our RAM has 16 memory locations. So it has, let's write them in hexadecimal. So 0H, 1H, 2H, 3, all the way up to the very last, which is FH. So what happens is, let's just say what we want to do. So how do we execute these instructions? What we want to do. So just, I think one of the rules that I saw from the Malvino book is that what happens is in your, I guess this is, how do we put it? In the least significant bits, or in your lower bits, the zero, let's say from in the lower bits, the data is you store your instructions in the low section of memory, and you store your data in the higher side of memory. So for instance, if you are storing your data, your instructions will start from 0, 1, 2, 3, 4, however long it is. Then your data will come on the other half. For instance, 8, 9, A, B, C. That's like memory location A, hexadecimal, B, hexadecimal. That's like 10, 11. So let's just run it. What do we want to do? So we have 16, 24, and 32. So the very first thing we want to do is we want to load data into the accumulator. And the data we want to load is 16. Next up, we want to add data to the accumulator, which we'll be adding 24. And next up, we want to subtract from the accumulator 32. And once we've done all that, we will want to output data, and then we will want to halt the system. Now, again, I'm going to say this is not an in-depth analysis. Think of this as more, I'm giving you inspiration to actually learn more. If you want to get an in-depth breakdown of how this works, this is found in chapter 10 of the Albert Malvino book. It's a really good book. You can look it, or if you have another resource, you can always just use it. So we see now so let's continue. Our instruction is stored from memory address 0 to memory address 4. So we have 5 instructions that we want to execute. Now, let's now proceed to, we have to store our data, because we can't have our data just as, we can't have it as 16, 24, and 32. That's not going to work. It's not how we would want to store our data. So we have to choose to store our data higher in memory, in higher addresses. So I'm going to choose to start storing my data from 8. So we'll store 16 in memory address 8. We'll store 24 in memory address 9. And we'll store 32 in memory address 10. And as such, we'd have to now rewrite this. So when we're loading the data, we'll not load 16, we will load the memory address. So we'll say load into accumulator the contents of memory address 8 hexadecimal. And the content of memory address 8 is 16. Then the same here, we'll now load from memory address 9 and load from memory address 32. So this is essentially what we want to do. This is what we want our system to execute. All right. So if we now translate this into, binary, just so that we can have a little bit of ease when we are programming the RAM, we know our load is 0, 0, 0, 0, and now we want to address memory address 8. That's just 1, 0, 0, 0. To add is 0, 0, 0, 1. Memory address 9, 1, 0, 0, 1. Next we want to subtract, which is 0, 0, 1, 0, and the data is stored in memory address 10, which is just 1, 0, 1, 0. Then the other two extractions for the out is 1110, and we are not loading any data, so it doesn't really matter what the lower bits are. And then finally halt, which is 1111, and that also doesn't matter because it does not handle any data. Of course, between 5, 6, and 7, the data there we don't really care about. But then at 8, we store the data for 16. So 16, I think, is 0001 0000. Then 24, 00011000. And then finally 32, 00100000. So now this is the data that we have to store in our RAM in order to get our system up and running. So now let's get onto our computer and program these exact values and see how that works. So in programming the RAM, we have this little switch here. So if we look here, we have two modes. So when we're in this mode, this is the programming mode, whereby I can easily set the address just using these buttons. So you see, if I change the deep switch, I go to memory location 0, then I can program it. Let's program, what is this? Let's program just all ones, and if I hit that, I program it. I've stored in memory location 0 that value, I think that's 255. But then the other option is having it be in, now that's run mode. So this is now the mode when the computer is running after it has already been programmed. So if we simply reset this with this control signal, this is the clear control signal, if you can see that, if we clear it, it goes back to 0. And look at that, we have, this is the address, this is what we stored in the memory address 0. So what we want to do is we want to store, because I think we'll be using, how many? We'll be storing from 0 to 4, we'll be storing the instructions, and then from 8 to 10, we shall be storing the data that we want to manipulate. So I'm just going to go through that. That one is, it's kind of like a bit, that's now the less interesting part of this exercise. So I'm just going to fast forward through it and program the computer, and then after that we can see how to work with the different control signals to program the computer. So let's just set it back into programming mode, and then let's start from 0. Let's just do at least the first one. So from 0, we know we're basically like just kind of like storing an 8, because the 4 most significant bits are just zeros, so we'll just have zeros over here. The first 4 are 0. All right, then we have a 1, and then the rest are 0. So basically this instruction is, the zeros is basically load into accumulator the contents in memory address 8. So let's program that, and now we have a memory location 0. We have that instruction. Let's just also do the first one. All right, so what's the first one? What we want to do, we want to add. So we know the first 4 significant bits, we have a 1 over there, then we shall have a 9 for the lower 4 bits. Then there we have it. So we have 0001 for add, and 1001 for what are we adding? We're adding the contents of memory address 9. So I'll just do the rest just quickly. Then we have what we expect. So now we've programmed everything. We've programmed all the data, all the instructions into the RAM, and we also programmed the data that we will be using into the RAM. So the instructions are in memory address 0 to 4, and the data is in address 8 to 10. So yeah, so now we can just take it back to 0. So now we're ready to program or to run our program. So one thing to note is we have to make sure all the registers, there's no register that is writing to the bus and there's no register that's reading from the bus. So if you look at all these registers, we have control signals. So for instance, this one is to clear. This is for the memory register, to clear memory register. This is to read into the read from the bus. This is to output the contents of the RAM. This is to read what's on the bus. All of them have those kind of control signals, which I think we'll be getting more in depth when we are dealing with when you run the program. So let's just get started. So the very first thing that we want to do is we want to start the program counting. So first of all, you start off by putting the contents. So we're putting the contents of our program counter onto the bus. Of course, since it's 0, you won't really get to see it. Also, the other thing I have to make sure is you have to make sure you're in programming mode. So the contents of the program counter are on the bus, and then we want to read that into our memory address register so that we call our first instruction. Of course, then the clock pulses. Let's just assume, or let's do this. Yeah, let's just leave it at that. We'll see how it works in the next round. So now we have put the contents of the memory. We have addressed the first program. We have called the first program, or we have latched the address of the first instruction. So we stop reading from the bus and we stop writing from the bus. And what our control signal does is now this is chip enable. We want to enable this chip. And the reason why we enable this chip is we want to increment the counter. So we increment the counter. So now the counter, you see we have done 1. So the next instruction will be calling from address 1. But that's neither there nor here. So now we disable the count, so that it doesn't really proceed. Of course, you wouldn't have done that. That's just for effect. So the next thing is, this is memory 0, and this is the instruction that we have. So the instruction is 000 load the contents of memory address 8. So we need to take this and put it onto the bus and deliver it into the instruction register. So how do we do that? We output onto the bus. You see now this data is on the bus, and we want to pull that data into the instruction register. So we want to use our read is active low. So our IR, read is active low. So now the clock pulses, and now we have our data there. So we stop reading from the bus and we stop writing to the bus. So all these things that I'm doing by manually, this is what the control logic would be doing. So now we have our instruction register. So in the instruction register, the 4 significant bits, the 4 most significant bits, this is now what goes to the control. Oh, you're not seeing. Yeah, so this is what we have over here, the instruction register. So the 4 most significant bits are what go to the control logic, but we don't have our control logic. Control logic is supposed to go over here, but I have not put it yet. Maybe once I'm done, then I'll make another video for that. So our control logic is saying load into accumulator. And what do you want to load into the accumulator? What we want to load into the accumulator is the data in memory address 8. So now we need to access this particular memory address. We need to access memory address 8. So what we have to do is we have to write this. We have to now access this memory. So to access this memory, we go and load the address onto the bus. So for the instruction register, it will only be loading the 4 least significant bits, because that's what has the address of the data that we want to access. This one will be going to the control logic. It doesn't go back to the bus. So now we have our data. It's back on the bus. Okay, and we want to, what do you want to do? Let's I'm just making sure I'm not making anything. So we want to read that data. We want that address. So this is an address to data that is stored in RAM. So we want the data in address 8. So let's now pull that. Let's get that address from the bus into our memory register. Something's not right, or I have not changed it here. There. And yeah, so now since we have already done that, so we stop writing to the bus and we stop reading from the bus. So now we have our address. So this is the data that we want, and this is exactly what we want, which is 16. All right, the data is 16. So what do we want to do now? So we want to load this data into the accumulator. So to do that, what we have to do is now we have to prime the accumulator for reading data. So to prime the accumulator, which is register A, we come here and we say we want to read from the bus. But what are we reading from the bus? We are reading from the bus the data in memory address 8. So now the memory address 8 is stored. It's being the data in memory address 8 is being put onto the bus. Now let's read it. And now we have read it. So the data is now in. So what do? You stop reading and you stop writing. All these different things that I'm doing, reading, writing, is what the control logic will be doing. And what we have, so at this particular state where we are at is, thank God. Yeah. So what I was saying, so I'm saying where we are at is that we are, we've loaded the data into the accumulator. So the accumulator has the data. What is the data? The data is 16. And if we look over here, we see, okay, it's showing 16 because that was the last data that we had read. Of course, if we refresh the clock, it will go back to 0, because there's kind of like a slight delay. So we're done with that, and after being done with that, everything else has been deactivated. So like, for instance, if I press, nothing is reading from the bus and nothing is writing to the bus. So let's go to the next instruction. The next instruction is what? We want to add the contents of memory address 9H to the accumulator. So what do? So now let's say now the instruction we want to call the instruction in memory address 1. So load that into the bus, and now let's the memory address. So let's call that. We want to load the instruction in memory address 1. The next instruction basically. So remember, so stop outputting, then increment. We increment our counter. That's okay. And then we take our data here, put it onto the bus and bring it down to the instruction register. So let's do that. Let's put it onto the bus. You see it's on the bus. Then let's read from the bus. All right, let's just go up. So that's the instruction register. This is the previous instruction. Now let's load the new instruction. We have loaded the new instruction, and what is the new instruction saying? 0001, most significant bit. That means add. If you remember our instruction set, add the contents of memory address 9. So remember, as always, what are we doing? We stop writing to the bus and we stop reading from the bus. And now we want to, now let's get this data, because we want to add the data in this memory location 9 into the accumulator. Now let's do that. Let's put the data into the bus. The data is on the bus, and we need to, this is now the address of the data we want to add to the accumulator. So let's get that data. Okay, it's been put, oh sorry, it's already now on the bus. Let's call it. All right, yeah, so now we have the data in address 9. All right, and so let's stop writing to the bus and stop reading from the bus. And what we want to do, remember, this is now what I want to do is now this is for add to the accumulator. All right, so we're adding to the accumulator, and that's now for me. I'm the one who's going to do now the whole manual running. So to add to the accumulator, we need to output this data. This is 24, so let's put 24 onto the bus. 24 is put into the bus. Now we want to add to the accumulator. To add to the accumulator, we access the data. We put the data in register B. This is register B. So let's put the data into register B. We have not used register B yet. So we're putting the data into register B. So we want to put the data into register B. So we want this data to come into register B. Okay. So let's do that. So, but there's something I have to maybe mention here. I just noticed that my sum register here is now kind of like subtracting. All right, let's just leave it at that. Just just to, so that's something that the control signal would be sure to do. But let's just run it just so that I can show you. All right, so we've loaded 24 onto the bus, onto the register, but we don't want to deal with 24. So we've loaded 24 into here, but this, what am I saying? Okay, we have loaded 24 into register B, but if you look at this is not addition, this is actually subtraction, and we are not interested in doing a subtraction. All right, so that's where now the control signal would know that we are not doing a subtraction, we're doing an addition. So the control signal will have to put this one into the right mode. So that's now it has to put this one in A. So I think I think in a previous example, so the control signal will be sure to make that add. So now we have added so this is what? This is 16 plus 24, which should come, so this should be a 30. So what do? Stop writing to the bus, stop reading from the bus, which is this one. Stop reading from the bus. I'm not writing to the bus and I'm not reading from the bus. But we can just, let's have a little bit of fun since you're already here. Let's output this content onto the bus. Put the content, we see what we have. This is just me just cutting corners. So we have a 40 over there, but if we were to subtract, we'd have, what would we have? We have a token 248. That's if we're using unsigned, but let's say let's use signed. We have -8, so because that's what we expect. 16 minus 24 is -8. So let's go back to the right data, which should be 40. So now what we have done is we have done the subtraction. Now we've done the addition. Now let's load that data into the accumulator. So we're already on the right step. So we've loaded the data into the bus. Now let's load it into the accumulator, so that the accumulator now has 40 in it. So when we load into the accumulator has 40. But now this data has changed. But you see, it's still not it's not going to change this. So there's still propagation delay. So this prevents there being a rest condition, because a rest condition is shown by this changes, then this changes, then this changes, then this changes. It keeps on changing infinitely. It's kind of like racing against each other. Which data changes first, which one changes next, but we're avoiding that. So stop writing from the bus. No, stop reading from the bus and stop writing from the bus. And thus that completes our what instruction is that? Our second instruction. So the next instruction is instruction number 3. Yeah, let's call it instruction number 3. Instruction number 3, whereby we want to subtract some data. So let's now, what do we do now? I think we should be okay. Let's call now address. Let's load the third instruction. So we take from the program counter and call the memory address. Let's call that. There, we have our memory address 3 and our instruction. And as always, stop reading from the bus and stop writing to the bus. Increment your counter. So we have gone now. What number is that? That's 3. Is it 3? Yeah, it's 3. So that's now where we'll get our next instruction. So disable your counter so that it doesn't proceed any further. Load this data into our instruction. So load it to the bus, and then let's write it to the instruction register. Write it to the instruction register. Let's just, so that the data is over there, let's just get the instruction register in frame there. And then you always remember the drill. Stop writing to the bus. No, this is stop reading and stop writing. Now we have our new instruction 0010. Subtract the contents of memory address. I think this is 10. Memory address 10. Okay, so let's load the memory address, because now we want the data of 10. Let's now retrieve the data of 10, because that's now what this instruction would say. So let's retrieve the data of 10. In retrieving the data of 10, we load the address that we want, the 4 least significant bits. We load it into the bus. There we have it on the bus. And then what do we do next? Once we have it on the bus, we want to load the memory address to retrieve the data. So let's load that. Now we have the data on there. We've loaded the data here. So stop writing to the bus and stop reading from the bus. So we need to transfer this data to our register B. And how do we do that? Put it on the bus and let register B retrieve it from the bus on the next clock cycle. So now we have the data 32, it's showing 32 here. So what we want to do, remember how that other time we were in the wrong, you are subtracting instead of adding. So now we are going to put the subtract instruction. So we want to subtract 32 from the 40 in our accumulator, and then that's the date, that's what we have. So it has already run that instruction. So we stop writing to the bus and we stop reading from the bus, and we will put this content onto the bus, the content of this the sum register onto the bus, and then we want to load that into our accumulator. All right, so on the next clock pulse, it loads it into the accumulator. Stop reading from the bus excuse me, and stop writing from the bus. Okay, so there we have done all the calculations. We have loaded, we've done the we loaded, we added, and now we have done the third instruction. We've completed the third instruction. What is the third instruction? The third instruction is subtract 32, or subtract the contents of memory location 10 from the accumulator, which is the contents in memory location 10 was 32. So we have subtracted 32. We subtracted 32 from what was there initially. So of course now it has changed, but now this is now the final. This is now at the end of instruction number 3. So now let's move to the next instruction. All right. So now for our fourth instruction. So let's, we now know the drill. Okay, so we have to load this the next instruction, and the next instruction is stored in memory address 3. So let's load the memory address 3, which is the fourth location. Kind of confusing, but let's load that. All right, and as always, stop reading from the bus, stop writing to the bus. Let's increment. So we'll get the next one from address 4. Then let's load this instruction onto the instruction register. Load the instruction into the instruction register by writing to the bus. Boom. Then, so it's already written to the bus. Now let's go here, down here, and we want to read from the bus. And there we have it. Okay, stop reading and stop writing. So in this particular case, this instruction doesn't deal with any data. So we're not going to, although this is 0, this could be any random set of bits. We don't really care. This is a don't care condition because we're not retrieving anything from memory. All we're doing is we want the instruction to output data. So 1110 from our instruction set was to output data. So how to output data is what we're going to do is we're going to go to the accumulator. Also the instruction. Anyway, we're going to go into the accumulator, and we're going to put the contents of the accumulator onto the bus. So the contents of the accumulator is on the bus, and then let's press our out, and then we have our output, and now it shows 8. That's the end of instruction number 4. And then let's go into our final instruction. Let's get the data from we have put the data already. So the data is being output. So now this is the end of instruction number 4. So now let's go into the hold condition. So now to go into the hold condition, let's stop writing to the bus. All right, and let's load the contents of memory address of now the next. Let's call the next program that we need to run according to our program counter is this. So let's load that to the bus. Okay, let's load that to the bus and then read from the bus. We want to read that content in memory address 4 and this increment our counter. And our counter has been incremented. All right. So let's load this instruction into our instruction register, and if we load it in, we get the data loaded. And this time around, what this data is, this is just the halt instruction. So basically just going to tell the system to stop running. Now I'm not sure, but I'm thinking what the halt will possibly do. I think this one I may have to look into it, because I think what you want the halt to do is you want it to halt and then have the data of the last data, because the halt stops everything. Because what the halt will do, so let's just output the data that we had before onto the bus, because we're not writing that into the bus. Output it, and then what the halt does is, you see here we have a halt signal. So that halt, when that halt is activated, the clock stops working, so you can no longer proceed to do everything. So at the end of the day, we have done everything and we've gotten our result. I'm not sure about that. I think I'll have to look into that and see whether it will output, because I think you'd want the halt to, when you halt the system, to put the last data that you had, which kind of now makes it feel like, what was the point of out if out and halt can do the same thing? Anyway, I was just going, let's leave it at that. Anyway, so now we have the result of our calculation. The calculation is done, and we have our result over here. And and that's just what we expected. We expected an 8, and we have received an 8. So that's how data moves. So maybe before I finish, the next question is, what happens when you want to go into the next, let's say you want to load now the next program cycle or whatever. What usually happens is, right now we're in halt, what happens is you have to clear everything. So let's start from here. You have to clear your instruction register. We have a clear. So we clear the instruction register. We clear the B register. Where's that one? It's this one. The B register is cleared. We clear our A register. That one is cleared. We can also clear our memory address register. It's cleared. And then we can also clear our program counter. So we reset. So we are ready to run the loop all over again. Okay. So we still have our previous data there because you've not yet refreshed. Then of course when you're ready, you can remove, or it's not showing the clock. So we cleared, yeah. So that's it. That's basically a running of as simple as possible computer. So I guess what I'm going to do now is all the different controls that I was doing, because I'm going to build the control logic to do all those, because it can be very confusing. Because sometimes if you are, for instance, let's say you're reading from the bus, okay, you're reading data from the bus, and then you forget to stop reading, and then you add data from another register, and then the clock cycle pulses, you could lose data. All right, so at least you get, it's just a simple appreciation of how does the computer work, how does data move within the computer. Like I said, this is like just the big version of it. I think I'll give my final thoughts once I finish building the computer. But so far, I'd say this I've enjoyed building this. I've learned a lot. Um, yeah, I've learned a lot. It looks like kind of like a small board, but this is like really, really a lot of work. These kinds of conduiting, ooh, that was kind of like really, 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 really stressful. The kit is not necessarily affordable, and I can understand if someone chooses not to buy it. But I would say even if you don't want to buy the actual kit, I've seen people. Well, I've seen interesting people who have built it in Minecraft, but you don't have to go that far. You can also just build it um in a simulating program. I think, is it Logic Sim? I don't know if it's Logic Sim, but I think Logic Sim. Yeah, I've seen people who have built it in Logic Sim. When you can also look at, I think there's the Ben Eater Reddit subreddit, so you can look at that and see various inspirations. But anyway, I just wanted to put this out there because being able to do this gives me a new appreciation of digital logic, very low digital logic, and I think it's kind of like solidified my foundation, and that's what I'm very, very happy about. So yeah, I always love doing practicals. That's what I love about engineering, being able to take theoretical knowledge and build something practical out of it. And yeah, I'll be sure to update once I've finished the full computer, and when I'm not like doing things manually, I will put an update and I'll show now the computer running, because there's the control logic and then a bunch of other stuffs to make it a little bit more interesting. Yeah, so until then, thanks for watching, and don't be shy to leave a comment or a reaction. I always love receiving feedback.